Now I'd like to present our next speaker, John Mainzer. He's the principal architect at the HDF group. He'll talk about some of the new VFDs, including the Onion VFD and the Mirror VFD, and also the VFD SWMR, which is a re-implementation of SWMR. John, I'll hand it to you.
Okay, let's see if I can share the screen here. And, all right, can everybody see everything?
Yes.
Okay, good. So, several things to go over. I'll be going kind of quickly, and there'll be some oversimplification, but I'll do the best I can. First, Mirror VFD, we already discussed that a little earlier today. The idea is to duplicate a file on a remote system while it's being written on a local system. Use cases are the obvious backup and analysis of data as it's coming in. You can see here a little block diagram that Jake Smith put together, as he's the developer on this. Two major components here. The splitter VFD has two channels, a read-write channel and read-write only. All of your I/O requests go through the read-write channel to the local VFD, which is typically going to be sec2, and that gives you your local copy. The write-only channel duplicates all the writes, sends them off to the Mirror VFD, which transports that across the net to the Mirror VFD writer, and then to the file system on the remote system. A few minor items to mention here. Current implementation is sockets-based. It's not optimized for performance. Hopefully it's good enough for people to decide whether this is a useful feature, at which point I expect we will be working on optimization. It's available in 1.10.7 and should be in 1.12.1. On to Onion VFD. The idea here is to add version control and provenance management to the HDF5 library. Now there are a couple design options we could have chosen here. One would be to make our version control aware of the structure of the HDF5 file. That would have been probably more efficient, but also would have been very difficult to maintain. So instead, we decided to go down to the VFD layer and conceptually just divide the HDF5 file into pages. And whenever you modify a page, do a copy on write. And for the duration of your edits to this particular version, make any further writes to that particular page go to the copied version, and then set up an index which maps logical pages and versions to the appropriate physical page. I have a little diagram here which will give you the basic idea. So you see version 0, nice and clean. Logical pages and physical pages match. In version 1, we added page 4 and modified page 0. So we allocated some new pages and set up the index to point to them. And in version 2, we did a few modifications, and you can see the same thing going on there. You'll note that I didn't say anything about where the physical pages were. Reason being, you have lots of options. We certainly haven't implemented all of these yet, but you could put those pages in the HDF5 file. You could put them in a single onion file, as we tend to call them, or you could have one additional file per version. Right now, we're just going with the single file, although there are arguments for all three of these organizations. Anywho, at present, the minimal implementation is in test and debug. Hopefully, it'll be ready to go pretty soon. Note that there's going to have to be a fair bit of tools work to make it truly useful, but this will at least allow us to demonstrate the capability. Going on to VFD SWMR. Had a lot of objectives in this particular redesign and reimplementation. From my perspective as architect, of course, improving modularity and maintainability was the most important one. but I can't very well sell that to the users. So we had a bunch of other things we wanted to try and do. First one is full swimmer or something close to it. Loosely speaking, full swimmer just means if you're the swimmer writer, you should be able to do anything that you would normally be able to do if you were just a normal HDF5 writer. The remainder of the objectives, pretty straightforward, and you'll see how we get to those in the subsequent slides. So I have here a conceptual overview of the cycle of operation. This is horribly oversimplified, but it'll get you the basic idea. Simply put, we let the writer take a regular snapshot of the HDF5 metadata. We do that once per tick. Tick is some user-defined amount of time. Typically, we use 3 or 4/10 of a second. Way we've written the software so far, you can get down to 1/10. We don't allow people to go below that. And then we write this snapshot to an auxiliary metadata file. On the reader side, we stack the VFDs so that if an IO request comes down to the virtual file driver layer, the first VFD it runs into is the specialized VFD SWMR reader VFD. It looks at that read request and says, well, is it metadata? And if it is, it's going to satisfy that read request from the snapshot it's currently looking at. If it's a raw data request, it's simply passed down through to the underlying VFD, whatever that one happens to be. And obviously, the readers have to go and check for new snapshots as close to once per tick as they can manage. To keep the metadata file from exploding, we allow those snapshots to expire after max lag ticks. And you'll notice that assuming the file system can keep up, writes become visible to readers within 3 ticks. So I have here, again, a quite oversimplified diagram of what's going on. You can see on the writer side, actually above the VFD layer, we generate those snapshots as close to once per tick as we can manage and write them to the metadata file. In terms of actual I/O to the HDF5 file, it's handled just the way it would be if you would open the file in write mode. So the appropriate reads and writes go down to the VFD layer and out to the HDF5 file as required. On the reader side, you can see how we've stacked the VFDs. The VFD SWMR reader VFD intercepts the metadata read requests and passes the raw data read requests down to the underlying VFD, which I think right now is hard-coded to sec2, but eventually it can be whatever. So, some comments on the implications of this design. The big advantage here is that most of the HDF5 library doesn't have to even know that it's doing SWMR. The metadata cache has to know, the page buffer has to know, and obviously the VFD layer has to know. But the rest of the library doesn't, and as a result, pretty much all of the features just work. There are some exceptions. The major ones are variable length raw data. And the problem there is with the current implementation, raw data is stored in global heaps, and the global heaps are accessed via the metadata cache. We may or may not be able to finesse this particular problem, but for now, you'll run into problems if you use it, so stay away from it. And of course, the correct solution is to move the variable length data down into the chunks, as Quincy discussed earlier. The other potential problem we have is if you have a very long-running API call, you could overrun max lag ticks. Solution there is to set max lag to something suitably large, or don't use long-running API calls. Now, of course, since the rest of the library can ignore Swimmer, that reduces our maintenance costs and allows non-Swimmer applications to avoid the overhead of Swimmer. Also, you'll note that the snapshots don't require POSIX semantics. So in principle, we can support NFS or any other non-POSIX storage system. Also, the snapshot design has the potential to run in parallel. We can't do it right now because it's going to require a parallel version of the page buffer, but there are other reasons to do that, and I hope that we'll get to that one pretty soon. So, finally, current status. The friendly user release for VFD SWMR is available now. We're only supporting Unix and Linux. Major issue here is actually the test code. We're working on that one. As a simplification for testing, the current version does a flush of all raw data at the end of each tick. I think for a lot of applications, that's what you would want. But if you really want to maximize your throughput, that's probably not optimal. So the plan is to make this configurable and upgrade our test code so it can handle the situation. Benchmarks. Haven't done a lot with it, and I wouldn't take anything I say here all that seriously, but here's the results I have so far. If we're talking about a relatively small number of large data sets, the overhead on the writer side seems to be nil. In fact, I've seen some results that I don't quite believe, where it seems to be a little bit faster with VFD SWMR than without. On the other hand, if we go to a large number, say 1,000 or so, smallish data sets with 2 extensible dimensions, the overhead can get very bad. We've seen up to roughly a factor of 2. I'm hoping that can be optimized and improved, but that's what I have at present. And sadly, no data yet on the reader overhead. For further details, you can see the announcement, and there's a mailing list. And the objective right now is to have our first production version available at the end of May. So that's what I have for you today. Comments, questions? Dead silence. Everything is either crystal clear or clear as mud.
Yeah,
Very
I think
clear
there's some
summaries. Mark put in the chat window.
Well, thank you, John, for your presentation. And